All right, last unit of the year dealing with electricity. So this one is a little bit different in that I'm jumping around again. So we're going to start with outcome number 2 first. So some things you need to add to your notes. Kinetic energy is the energy of motion. Okay, and so here we're looking at electricity principles and technology. So important things to note in your notes is that electrons, E minus, remember that from earlier on. You don't need to write down the word electron anymore. Electrons can move. Now, electric charge can be found naturally in lightning and static. It could also be used to do work in computers and light bulbs, and your phones, of course. Now, the word electron actually comes from the word amber, and that's because the first person to discover uh, the effects of electrons was this king. He was polishing, king slash philosopher. He was polishing up this piece of amber. That's kind of like, Jurassic Park, the yellow stuff. And as he polished it, he noticed it attracted more dust to it as he was trying to clean it. And the word electron, that's the Greek word for electron, and that's where electricity, the word comes from. And by the way, I'm not sure if I mentioned it yet, electrons are negative and they can move. All you have to do is rub your hair and you're moving electrons. Touch a wall, you're moving electrons. Well, let's look at how to produce charge. Materials that attract and repel each other are said to be charged. It's produced by transferring electrons from one object to another, by rubbing, touching, or moving close together and then separated. We looked at producing charges when we were in the chemistry unit. Metals give electrons away to become positively charged. Non-metals absorb electrons to become negatively charged. So, for example, it has to be two different materials, though, if you're transferring charge from one thing to another. If you rub two identical socks together, nothing's going to happen. You might make some funny noise, but that's about it. But if you rub a cotton and a wool sock together, one of them is going to be better at pulling electrons, or if you want the fancy word, one of them is going to be more electronegative. And so then one becomes plus, one becomes minus. This happens when you rub your socks against carpet. You build up static electricity. This happens when water and ice crystals collide and rub against the air that's up there, and they transfer charge that way as well. And here is the young lady touching the Van de Graaff generator. She's building up charge, and her hair is all standing out. We do have this device, so I'm hoping we managed to stay in school in order to be able to use the Van de Graaff generator. I'm reminding you here, if you gain electrons, you become negatively charged. If you lose electrons, you become positively charged. And of course, as you're going through this video, if you need to pause it to fill in your notes, there's nothing preventing you from doing that. An electroscope is a device used to measure electric charge. It's really just two pieces of aluminum foil hanging off of a little cable, and if there is electric charge on it, the leaves move around. Static electricity is produced by rubbing or touching objects that remain stationary, and then static charge remains stationary. So if you take a balloon and you rub it on your head, that part where you rub on your head develops a static charge, not the rest of it, because balloons are not good conductors, unless, of course, you use a metal balloon. If you rub a metal balloon on your head, yes, it'll build up a charge in one spot, but then that'll spread over the entire balloon. Someone's saying, where do you even get metal balloons from? They sell them at the Looney store. They're usually the ones that they fill up with helium. An unbalanced charge is a better way to describe static electricity because, yeah, static electricity builds up and builds up, but eventually it discharges. And static means never changing. So that's not a great way to describe it. But unbalanced charge, a charge produced by rubbing or touching and transferring electrons, those can go back into balance by moving electrons around. And so that is a better way to describe it. Now, charge is measured in a unit called coulombs. Okay, and to give you an idea, a 100-watt light bulb has 1 coulomb per second going through it, and the charge on one electron is 0.0, and then there's 18 zeros and then 16 coulombs. That's a charge on one electron, or if you want, negative 1.6 times 10 to the minus 19 coulombs. What's the charge on a proton? It's the opposite, plus 1.6 times 10 to the minus 19 coulombs. And so there is a cool video, Bill Nye, on static that you should watch. I can't play it here because then YouTube gets angry at me. But the video on static electricity is available on YouTube itself, so you could always go there and watch the video. Okay, so making sense of electric charge. There's three conditions relating to electric charge, and once again, it's caused by the movement of electrons. Something could be neutral, and if it's neutral, has equal number of plus and minus charge. Something could be positive, which means it has more positive charge than negative charge, or if you want excessive positive charge. We're grade 9, so we know it's electrons that can move around. So if something's positively charged, it loses electrons. I think I spelt that wrong. Something that's negatively charged, there's more negative charges than positives, so it has excessive negative charge. That means it gains electrons. So if we look down at this one, equal amounts of pluses and minuses, right? And so in that case, the charge is, overall net charge is zero charge. In this case, pluses and minuses cancel. Some of them do. This one's gone. This one's gone. This one's gone. And what am I left with? I'm left with pluses, and I'm left with plus sixes. So the charge on that is plus 6. This next one, these two go, these two go, this goes, and I'm left with minus 4 charge. Okay, and we know from chemistry that positive particles in the atoms are called protons, the negative ones are called electrons, and the negative particles are the ones that are zipping around the outside nucleus. That's why you can move electrons easily. You cannot move protons easily. If you move protons, you are doing a nuclear change, and watch out, there'll be a giant explosion as all the energy is released. But electrons, easy to move. Here, I'm rubbing what's left of my hair. I'm rubbing the tabletop. I just transferred electrons. It's as easy as that. If I charge a balloon, I can touch. Well, it's hard to get rid of charge on a balloon. You'll see that in class when I do the demonstration. And there's a picture of me and my balloon friend. That's a picture of me and a plant. These are pictures from when we were totally shut down during COVID last March. And I took a picture daily to let the kids know I was actually still around. Okay, so then if neutral fur is rubbed on amber, some electrons leave the fur and make a positive. So here you can see both equally charged, both neutral. And you can see in this picture, only the minuses can move, and these minuses, these ones here, have moved onto here. So the rod has a -2 charge, the wool has a +2 charge. And we know, what do we know about opposites? Opposites attract. And so there is an attraction that happens there. And there's these 3 laws of charges that you need to memorize. Okay, so put a star beside them. It's important that you know these. First one is that unlike charges attract, or if you want, opposites attract. Now that's easy. That's a saying in society. You probably don't need to think about it too much to remember that one. And then similar charges repel. And I will, of course, show you some stuff in class. We'll do some lab work with this, so you'll be able to know that. But I mean, this is just the opposite of the other one. The one that everyone seems to forget about is the one that everyone knows about. Since you were probably a little kid, you've rubbed balloons on your head, put it up to the wall, and it sticks. Charged objects can actually attract neutral objects. And it's called charging by induction. And so here's how it works. If I have this balloon that's negative and I bring it close to the wall, the minuses in the wall all go out here. That leaves the surface as being plus, and then they can then attract. Now, can this be done, make a permanent charge? Because as soon as you pull that balloon away, these negatives are just going to come back. Well, if you push it close by and you push the negatives there, and then you take a samurai sword and you chop the front of this off, this part will remain plus, that part will remain minus. You can actually do charging by induction. Now, there's 4 classes of materials in electricity. The first one is the insulator. Insulator is a material that does not allow charge to move freely on them or through them. So rubber, cotton, glass, pure water does not conduct very well. And then you have the conductors. These are materials that allow charges to move freely through them. Like there's copper, aluminum, gold. And then we have something called resistors. They allow some charge to flow through, but not all. And so, like pencil lead, classic one. You have resistors, of course, in your electronic devices to control the amount of electricity. That's why your phone feels hot when you start to use it. And finally, they have superconductors, materials that offer little or no resistance. This was an interesting one. A fellow who's making super fridges and then testing how metals and other material react at lower temperature found that the colder he made the metals by building better fridges, the more electricity flowed. And so he accidentally discovered the superconductor. IBM, International Business Machines, is doing the research on this. If they get this to work, and it works right now, it works at about minus 120 degrees Celsius. If they could get this to work at room temperature, IBM would replace every electronic device maker overnight because their phones and their computers would run so slow. Essentially, with a superconductor, you get the electricity going pretty close to the speed of light if you want to. It's used in generators, power lines. Some super high-end computers might have superconductors in them today. Now, there's several methods of neutralizing unbalanced charge, or to discharge them is the fancy word. So discharge means to remove the charge. Okay, so if something has too much minus, it's going to discharge it, you got to get the minuses off of it. If something has too much plus, you actually have to add electrons to them to discharge. In all cases, it's electrons moving to make the charge balanced again. So if you're, here's some classic examples. Jumping up and down on a trampoline, right? The trampoline is insulated from the ground. You're jumping up and down and you're rushing past the air. So you're building static electricity. When you then step off, you get this big zap as electrons move to bring you back to a neutral position. Or these big rigs, as they go down the highway, they're rushing past this air. All the static is building up on it. You don't want it to build up on the truck. It could explode. And so they actually have one of two things. Some of them have these like this spike up on top of it. And as it's going down the highway at nighttime, if it's really dark, you can actually see the purple glow that's coming off of it. The other one that's more likely for you to see is they have these chains that hang down, but they don't quite touch the ground. And every now and then at nighttime, you could see them sparking. You'd think that it's the chain hitting the ground, but it's actually electric sparks jumping from the chain down to the earth as they try to become balanced charge again. Okay, and gasoline trucks, when they come in, they always ground themselves first. Because imagine you pull in with your gasoline truck, it's all full of static electricity. You take the hose and put it to the big underground tanks, spark jumps, and it could cause a fire, which could then, be devastatingly explosive to the gas station. And there's me with my balloon again. Non-conductors or insulators must neutralize if you want. So for example, let's try this again. If you got static electricity on your clothes, you can use ionizing devices to produce both negative and positive ions here, or you can use like Static Guard or Hero. Hero is kind of interesting. If you have static cling, you either have too much plus or too much minus on your clothes. In Hero, or if you want Static Guard, it's full of pluses and minuses. When you spray it on, let's say my clothes were full of minus, the pluses get attracted to it to neutralize it, okay? And the minuses get repelled. But you're probably thinking, yeah, okay, fine. But what happens if I spray it till there's no more static cling? How come nothing else happens? Well, after your clothes become neutral, the pluses, the minuses that are coming out of the can just sort of interact with each other and nothing else happens. Buildup of static electricity could be good and could be bad, okay? Some cases where it's not so good, dust builds up on TV screens and TV screens, and your clothing can attract dust. Some good things about static is also bad for your electronics. It shortens their lifespan. Some good things about static, though, the photocopiers work on static. They actually put a layer of static on essentially a plate, and then the paper goes over it, picks up the static, and then it blows the ink across, which sticks to wherever the static is, and then they heat it, which is why your photocopiers always come out warm. There's electrostatic painting, We have electrostatic sprays and coatings to help prevent static development. In fact, on computer chips now, they have the coating. Some people have super high-end computers will always ground themselves before they use their computers. And so in that sense, it prevents the static from slowing down their computers. Now you've seen how the attraction between positive and negative charge works. So that was all static electricity or unbalanced charge. In the next topic, you're actually going to go ahead and see how we can use current electricity in wires and use them to do work a little bit more so than with static. The problem with static is it builds up discharge, builds up discharge, builds up discharge, whereas current electricity is a continuous flow of electricity. So it's a lot easier to manage and control than to try and do that. The same electrons, though, that cause static electricity are the same electrons that are running through a wire. At this point in time, you would stop and do page 271, numbers 1 to 7, or you would do your adapted assignment. And so there it is, outcome 2, part 1 notes.